Hello lovelies, in this video we're going to be going through the AQA A-Level Maths Paper 2 that we've written for 2024. So what I'm going to be paying attention to in this video is the clues that we've left you when we're writing the question, and then how we've responded to those and how we've structured our answers as we're going through all of the questions.
This question asks us to prove that there are an infinite number of prime numbers. So the first thing we want to do is to assume that this statement is not true and that there are actually a finite number of primes. In fact, we're going to say that there are n primes. And we can write these down and list them. We could say that there's P1, there's P2, there's P3, there's Pn-1, and there's Pn. So there's n different prime numbers. What we can do now is we can multiply all of these prime numbers together, and let's call it P, capital P. So that's P1 times P2 times P3, all the way up to timesing it by Pn. So P is a multiple of every prime number in that list. Now for our next step, let's have a go at adding 1 to this value P. Okay, so we're going to say that P plus 1 is equal to P1 times P2 times P3, on and on and on, until eventually you times it by Pn, but then it's going to be plus 1, okay? So P plus 1 should not be a prime number because the only prime numbers that exist are the ones we've written down here, P1, P2, P3, P4, Pn. And so what will happen then if we divide P plus 1 by one of these prime numbers? So let's imagine for our next step that we take P plus 1 and we divide it by, say, Pn. Or in fact, any of these prime numbers, it could be P1, P2, whatever. If we divide this P plus 1 by Pn, for instance, we will always get this remainder of 1. And as there are no integers that will divide 1 other than itself, this value of P plus 1 must be a prime number too. And this is going to contradict our original assumption. So we can say that we have proved by contradiction here that there are actually an infinite number of primes. And our final statement will simply be that this fact, that whenever we divide by Pn we get a remainder of 1, contradicts our assumption that we have a finite number of primes, and so there must be an infinite number of primes. And this specific proof is a specific one that they could ask you in your exam. Obviously there's lots of different proofs they could ask you that vary slightly, but this is one sort of model proof that definitely could come up in your exam. So if you don't know this proof off by heart, then this is the video for you. Make sure that you go away, make notes on what we've said, and that you get it memorised, because you don't want to lose 4 marks in the exam when you've had it right in front of you here. The diagram shows a sketch of part of the curve with equation y equals x times x plus 2 times x minus 3. The region R1 shown in the diagram is bounded by the curve and the negative x-axis, and we're being asked to show that the exact area of R1 is 16 over 3. So to answer this, we need to know that we can get the area under a curve by integrating, and in this case we would need to integrate between 0 and whatever the coordinate is of this point here where it cuts that x-axis. Now, curves cut x-axes when y is equal to 0. So if we take the curve x brackets x plus 2, x minus 3, and we equate it to 0, we can see that we get 3 solutions. We get x equals 0, x equals minus 2, and x equals 3 as well. So that means, looking at this curve, that this coordinate that we need is when x equals minus 2. So that means that we have enough information to fill in now on our graph to then be able to go forward with our integration. So we know we need to integrate this curve. Now I find that in the second year of A-level, A lot of people get confused when they see a basic integration like this. They see the brackets and they think it's something a lot more complicated. Whereas actually all you need to do to start is just multiply out the brackets, and then it's a normal polynomial integration. So it's a gift really. I'm going to start by multiplying out these double brackets. And here I find that the double brackets give us x squared minus 3x plus 2x minus 6. So let's give this a simplify. So now we have the integral of x times by x squared, and then grouping up these like terms, we get minus x and then minus 6. And we need to integrate that with respect to x. Now, a little bit more simplifying, and then you'll see how easy this is. We just need to multiply out this bracket now. So we get x cubed minus x squared minus 6x. And we need to integrate that with respect to x. So hopefully you remember that when we integrate a basic polynomial like this, you add 1 to the power and then you divide by that new power. So here we have got the integral between the limits of 0 and minus 2. We've got x to the power of 4 and then divided by 4. And then minus x to the power of 3 divided by 3. And then minus 6x to the power of 2 divided by 2. And we need to substitute in 0 and minus 2 here. So we always start with that upper limit. So we've got 0 to the 4 over 4 minus 0 cubed over 3 minus 6 times 0 squared over 2. And then we're going to subtract from that minus 2 to the power of 4 over 4. Now I can't express enough, be careful with brackets here with these negative numbers. And then minus 2 cubed over 3. And then minus 6 times minus 2 squared over 2. And we just need to put this into the calculator now. However, please be careful of brackets with those negative numbers, because if you make a mistake here, probably it's due to one of those. So putting that into the calculator, I get 16 over 3, which is of course what we needed here. So now we're told that point B corresponds to the minimum of the curve, and we're asked to find the x-coordinate of B. Now what we need to remember here is any mention of minimum or maximum or turning points tells us that we need to differentiate and then put equal to 0. Let's start off by reminding ourselves of the equation for y. So we know that y was equal to x cubed minus x squared minus 6x. And to differentiate, we just multiply through by the power and then take one away from the power. And that of course gives us here 3x squared minus 2x minus 6. So we mentioned above, didn't we, that the minimum point of the curve corresponds to a point where that gradient, or dy dx, is equal to 0. So what I'm going to do next is I'm going to take this formula that we've just got for dy dx, and I'm going to put it equal to 0. So here I have 3x squared minus 2x minus 6 equals 0. Now, this isn't going to factorise. I'm going to use the quadratic formula. So I'm always like to take things slowly with quadratic formula to minimise mistakes. And even though we're at A level, I'm still going to say that A equals 3, B equals minus 2, and Z equals minus 6. And writing down my quadratic formula, I've got x equals minus b plus or minus the square root of b squared minus 4ac all over 2a. And substituting in our values here, I have minus 2 plus or minus the square root of minus 2 squared, don't forget the brackets, minus 4 times 3 times minus 6, all divided by 2 times 3. So putting that into the calculator, I get 1 plus root 19 over 3. Or I also get 1 minus root 19 over 3. Now it can't be both, can it? What we should do here is look at the diagram in this case, and we can see that the x-coordinate of b is clearly a positive value. Therefore, we can eliminate the negative value of 1 minus root 19 over 3, leaving us with an x-coordinate of 1 plus root 19 over 3. Here we're told that the function f of x equals ax cubed minus 3x squared plus bx plus 20 for all real values. We're told that x plus 4 is a factor of f of x. And we're also told that when f of x is divided by x minus 2, it leaves a remainder of minus 54. So because we know that x plus 4 is a factor, we're going to use the factor theorem. And factor theorem states that if x minus a is a factor, then f of a will equal 0. Now, in addition to that, we're also able to use something called the remainder theorem here. We were told in this question that when f of x is divided by x minus 2, it leaves a remainder of minus 54. So let's remind ourselves of what the remainder theorem is. So if f of x is divided by some factor, let's call it x minus a again, then fa would be equal to that remainder. Now, these are two really important facts which are critical to this question, and so if you didn't know them, make sure you make some notes on them now. But let's first look at this statement that x plus 4 is a factor of f of x. And let's therefore substitute in x equals minus 4. And we're going to equate that to 0 once we do that. Okay, so f minus 4 equals a times by minus 4 cubed minus 3 times minus 4 squared plus b times minus 4 plus 20. So tidying this up, I get minus 64a minus 48 minus 4b and then plus 20. And I know that that is all equal to 0 thanks to the factor theorem, okay? Really, really, really important that we remember that. So here then we can say that we've got minus 64a minus 4b minus 28 equals 0. So now we've done that for the factor theorem, we can now look at the second statement and think, okay, let's use remainder theorem now. So I know when f of x is divided by x minus 2, we get a remainder of minus 54. So let's substitute in 2 into this then. So I've got a times by 2 cubed, minus 3 times 2 squared, plus b times 2 plus 20. That gives us 8a minus 12 plus 2b plus 20. Tidying that up a touch, I get 8a plus 2b, and then minus 12 plus 20 gives me plus 8. And because of the remainder theorem, I'm going to put that equal to the remainder of minus 54. So now I've got two equations in terms of a and b. And so that classic maths topic of simultaneous equations is going to be what solves this. Let's write down those two equations again so that we can put them side by side. So to start us off here, we have minus 64a minus 4b minus 28 equals 0. And underneath that, I'm going to write 8a plus 2b plus 8 equals minus 54. Now, like I mentioned before, because I've got two variables here, I have a and I have b, I can do simultaneous equations. Now, at first glance at this first equation, I've numbered them 1 and 2. First equation, I can actually simplify this a bit. I can see that I can divide this down and I can halve this. That will end up giving me then minus 32a minus 2b minus 14 equals 0. And if I now put that alongside equation 2, which was 8a plus 2b plus 8 equals minus 54, I can see that critically the b's are kind of the same. They're both 2b. One is a negative and one is a positive. So if I end up adding those to each other, they will cancel out. And so if I add these to each other, minus 32a plus 8a gives me minus 24a. Like I said, the b's will cancel. Minus 14 plus 8 gives me minus 6. And 0 plus the minus 54 gives me minus 54. So if I rearrange what we've got here now, let's add the 6 to each side. I get minus 24a equals minus 48. And so if I divide by the minus 24 now, I see that a is equal to 2. So we now know what the value of the a is. Now we simply need to substitute this into any of our earlier equations to find out what b is. So I think that equation number 2 is probably the easiest one here. However, they will all give you the same outcome. So 8a is now 8 times 2, and then plus 2b plus 8 equals minus 54. So let's tidy this up now. I know that 8 times 2 gives me 16. And then if I add on the 8, that gives me 24. So now I've got 24 plus 2b equals minus 54. Let's subtract 24 from each side there. That gives me 2b equals minus 78. And if I divide through by 2, I end up finding that b is equal to minus 39. And so there we have it. Now we know what b is as well. So that is A done. We know that A equals 2 and B equals minus 39. So now if we go back to B now, our next part, we're asked to write f of x as a product of 3 linear factors. And the method that we're going to use to do this is going to be algebraic division. And this is a very common pairing with factor theorem. So very much expect after a factor theorem question to then have to follow it with doing some algebraic division to find the other factors. Now in this case, we said that A is equal to 2 and B equals minus 39. And so in order to do any algebraic division here, first off we're going to need to substitute those values into our f of x equation so that we have the full form of f of x. So here I'm going to have f of x equals 2x cubed minus 3x squared minus 39x plus 20. And we're going to divide that by the known factor. And we were told that it had a factor of x plus 4. So we're going to divide this function by x plus 4. And this method is always quite it's a tricky method. There's a lot to it. I always find that you just got to keep the momentum flowing with it and don't overthink it. Okay, so let's get started. We ask ourselves how many x's go into 2x cubed? The answer to that is 2x squared. Now we're going to multiply that 2x squared by the x, gives us 2x cubed, and we write that directly underneath. Then we're going to do 2x squared times by 4, and we write that directly underneath the x squared, so that gives me plus 8x squared. See how we're keeping the cubes all in one column and all the squares in one column and so on. So the next thing that we do here is we're going to subtract these from each other. 2x cubed minus 2x cubed just goes away, it gives us 0. But then minus 3x squared minus 8x squared gives me minus 11x squared. And that's what we're going to use for our next step. And this is hopefully where you start to see a pattern. So now we ask ourselves how many x's go into a minus 11x squared. So the answer to this is minus 11x. So we put that up here. And now again, we're going to repeat things. First off, I'm just going to lower down the minus 39x. You don't have to do that, but I find it helps. But now we're going to do exactly what we did before. So minus 11x times by x gives me minus 11x squared. So I'm going to put that in my x squared column. Now minus 11x times by 4, that gives me minus 44x, and I put that in my x column. Now again, I'm going to subtract these. Minus 11x squared minus minus 11x squared gives me 0. However, minus 39x minus minus 44x gives me 5x. So now we do the same again and we ask ourselves how many x's go into 5x. Well, it only goes 5 times, so I put plus 5 up above now. I'm going to lower down the 20 just so it looks a bit nicer. And now I'm going to do exactly the same as before. I'm going to multiply that 5 by the x, and I'm going to write that in the x column, so 5x. And I've got 5 times by the 4, which gives me 20. So I put plus 20 in my numbers column. Now I subtract them and I get 0. And that's important because that's shown that everything has divided into it perfectly. And it is basically the factor theorem is shown. It is definitely a factor. So now we can rewrite this as a product of a linear and a quadratic factor. Sometimes that's all you can do, but the fact they said that we have 3 linear factors tells me I can factorise this. I'm going to have a go at doing that. I'm going to put a 2x in one bracket, an x in another, and a minus 1 and a minus 5, and I can see that that is the correctly factorised version. So therefore, my 3 linear factors are x plus 4, 2x minus 1, and x minus 5. And there we have it. We have written f of x as a product of 3 linear factors. A circle C has 2 points A and B at opposite sides of its diameter. Point E has coordinates a minus 2, and point B has coordinates 7, 5. The tangent to the circle C at point A has the equation y equals minus a half x minus 3. Find the equation of the circle C. So I'm starting off by labelling on a bit of information here. I know that point A has the coordinates a minus 2 and B has the coordinates 7, 5. I also know that the tangent to the circle C at point A has the equation y equals minus a half x minus 3. So what I'm going to do here is, just to visualise it, I'm going to draw that tangent on. And I know that the equation of that is y equals minus a half x minus 3. Now this can really help us because the tangent at A is going to have the same coordinates as the circle at that point A. So that is definitely going to come in handy when trying to work out the equation of this circle. Before we do anything else now, just remind ourselves of what the general equation of a circle is. Now this is something that we do need to have memorised, so if you don't recognise this, then do get memorising it. In this case, A and B are the coordinates of the centre of the circle, and R is the radius. So we need to work out the coordinates of the centre of this circle and the coordinates of this radius too. Now in order to do any of that, we first off need to know what this coordinate of A is. And this is where knowing the equation of this tangent comes in. Because of course the equation of the tangent and the circle have the same coordinates at A. So we can substitute in y equals minus 2 into this equation of a straight line and solve it then for x, or in this case, A. So we need to get A all on its own. The first thing I do here is add 3 to each side. That ends up giving us 1 equals minus a half A. And then I would divide through by minus a half or multiply through by minus 2 to get the A on its own. And that gives me A equals minus 2. So now I know that the coordinates of point A are minus 2, minus 2. Now we have enough information to work out the midpoint of this line. So for this reason, we're going to be able to work out what A and B are in this general equation of a circle. So to do this, we need to remember how we calculate the midpoint of 2 points. The midpoint we find by adding the two x coordinates either side of this diameter and dividing it by 2. We're essentially finding the average or the mean. And then for the y's, we do y1 plus y2 and then divide by 2. So we're just basically averaging the x and the y coordinates of either side of that diameter. So putting the numbers in now. Here we're going to have our minus 2 that we just worked out, plus 7, the x coordinate of B. And then once we do that, we're going to divide it by 2 because we have 2 values. Then for the y coordinate of our midpoint, we're going to take our minus 2, which is our y coordinate of A. Then we're going to add the y coordinate of B, which is 5. And then again, we divide it by 2. So simplifying this now to get the midpoint, I get 5 over 2 and 3 over 2. So those are my coordinates of my midpoint, where 5 over 2 is the x coordinate of the midpoint, so that would be A in our equation above, and the y coordinate of the midpoint is our 3 over 2, which is B in our equation above. So looking good, huh? We have now got the first half of this equation, the whole of the left-hand side is completed, but we need to know what the radius is to complete this. So there's a couple of ways we could do this. We could either work out the length of the diameter and then halve it, or we could work out the length of the radius straight off. Both ways will get us all of our marks, so don't worry about that. So if we choose the distance from A to the centre, we should know that to work out the length of a line that joins two coordinates, we essentially use Pythagoras' theorem. Okay, so we can say that R, in this case this radius, is going to be equal to the square root of y2 minus y1, and then square that, and then plus x2 minus x1. And again, we square that as well. So that there is our Pythagoras' theorem that is going to work out the radius of this. So in this case, let's remember what coordinates we're using. So we said that we're going to use the point A, or we could use B, and we know that that has the coordinates -2, -2. And let's use the midpoint because then we get straight to the point. So we've got 5/2, 3/2. Although, however, like I said, you can work it out for the diameter and then halve it. So the change in y squared is going to be 3/2 minus -2 squared, and then plus the difference in the x's squared, so that's 5/2 minus -2 squared, and then all of that is square rooted. So if I put that into the calculator, I end up getting root 130 over 2. So that is our radius. So now we've got all of the individual parts that we need to be able to put into our general equation of a circle. So we know that A is 5/2, so let's get started with that. So here we're going to have x minus 5/2 squared. That's our first part. And then we know that B is 3/2. So we're going to have plus y minus 3/2 squared, because of course B was 3/2. And then that's equal to the radius squared, which is going to be equal to root 130 over 2 squared. And we would want to simplify that bit. So here I've got x minus 5/2 squared plus y minus 3/2 squared equals 65 over 2. And there we have it. That is our equation of the circle C. The equation 3x cubed plus x squared minus 1 equals 0 has exactly one real root. Show that for this equation, the Newton-Raphson formula can be written as xn plus 1 equals 6x cubed n plus xn squared plus 1 over yxn squared plus 2xn. So we should know that when f of x equals 0, which is what we have when we have a root, which is what's being talked about in this question, xn plus 1 is equal to xn minus f of xn over f dash of xn. Now in this case, we know that f xn equals 3xn cubed plus xn squared minus 1. F dash xn tells us to do the differential because that's what the dash represents. So differentiating this and multiplying through by the power and taking 1 from the power, we get 9xn squared plus 2xn. So we've got everything we need here to just substitute this into our Newton-Raphson formula. So we've got xn plus 1 equals xn minus 3xn cubed plus xn squared minus 1 over that differential 9xn squared plus 2xn. So we've got something here looking very, very nice. You can see it's not quite what they wanted though in this show that. And that's where the show that can guide us. It's never the thing to lead us, but it can certainly guide us. Let's try and rewrite this as a single fraction, just like the show that wants. So let's take that xn and times the top and the bottom by the denominator. So we're timesing top and the bottom by 9xn squared plus 2xn. So timesing that by xn, we get 9xn cubed plus 2xn squared. And then bearing in mind that we've got one denominator now, we've got minus 3xn cubed, and then minus xn squared, and then minus 1, so plus 1, and that's all over that common denominator of 9xn squared plus 2xn. Just to remind you of what I've done here is I got two fractions by getting the xn to have that denominator of 9xn squared plus 2xn. And then whenever we have common denominator and we add or subtract fractions, we can just add the tops or subtract the tops and then just keep it with that one single denominator. So that's what we've done here. And now we should be getting a bit closer to what we were wanting to show. having a look here, if we simplify, say the x cubed terms first, here we've got 9xn cubed minus 3xn cubed, which leaves us with 6xn cubed. And then looking at the squared terms, we've got plus 2xn squared minus xn squared, which just leaves us with 1xn squared. And then a plus 1 on the end. And that's all over 9xn squared plus 2xn. So we have done it. We have showed that formula. Okay, so now using the formula with x1 equals 1, find the values of x2 and x3. And the great thing is even if you couldn't successfully do A, because it's a show that, we can still do everything else using the formula that they gave us. So if we know that x1 equals 1, then x2 is going to equal 6 times that x1, so 1 cubed, plus 1 squared, plus 1, over 9, 1 squared, plus 2 times 1. So everywhere where it would have been x1, we have substituted in that value of 1. Now putting that into the calculator there, I end up getting an x2 value of 8 over 11. So now that's what we're going to use to work out what x3 is. Because x3 will equal 6x2 cubed plus x2 squared plus 1 all over 9x2 squared plus 2x2. So let's swap those in. So here we have x3 equals 6 times 8 over 11 cubed plus 8 over 11 squared plus 1 over 9 times by 8 over 11 squared plus 2 times 8 over 11. Well, that's definitely worthy of a calculator, that one. Would not want to do that in my head at all. So when I do put that into a calculator, I end up getting a rather large fraction of 5,107 over 8,272, which is about equal to 0.617. So there we have it, okay? Let's have a look at C now. So in this case, we're not able to use x1 equals 0 in the Newton-Raphson method. Suggest why. So if we have a look at our formula, and more specifically, we have a look at the formula for the differential. So we know that f dash x was equal to 9x squared plus 2x. Now you'll notice there that there is a stationary point at that point of x equals 0. Therefore, we can't use x1 equals 0. It's a stationary point. It's not going to properly cross through the axis at that point, and that's what we need with the Newton-Raphson method. So the reason why we can't use x1 equals 0 is because there's a stationary point at x equals 0. Know that whenever they say something like that in a question, and it could be for any function, have that as your first thought, okay? Think, is there a stationary point at that point? Could that be why? Double check it, and in all likelihood, that is probably the correct answer. So if you didn't know that, then make a little note of it. It's one of those few cases in maths where a little note really might help you out. Given that y equals 5 sine theta over 2 sine theta plus 2 cos theta, show that dy d theta equals a over 1 plus sine 2 theta, where a is a rational constant to be found. So what we need to recognise here is we have a quotient rule question. And that's because our function here, it's got something in terms of theta over something in terms of theta. And the general equation you would have learned would be dy dx equals v du dx minus u dv dx over v squared. Now in this case it's going to be dy d theta, not x. So let's write down what we have. The u is the bit on the top, so u equals 5 sine theta, and the v is the bit on the bottom. So here v equals 2 sine theta plus 2 cos theta. Now we need to differentiate each of these with respect to u. Firstly, we need to differentiate 5 sine theta. We should recognise that sine theta differentiates to cos. So in this case, du d theta is simply 5 cos theta. Next up, we need dv d theta. So 2 sine theta, again, sine differentiates to cos. So that just gives us 2 cos theta. And cos differentiates to minus sine, so we get minus 2 sine theta at the end there. Now, substituting these all into our equation above, the standard form, dy d theta will be equal to v, which is 2 sine theta plus 2 cos theta, times by, in this case, du d theta, which is 5 cos theta, minus u times dv d theta, so that's going to be minus 5 sine theta times by dv d theta, which is 2 cos theta minus 2 sine theta. And then that's all over v squared, which means that's all over 2 sine theta plus 2 cos theta. And that has to be squared. Okay, so there we go. Got a big, messy looking thing here, which we need to simplify. And we'll start off just by multiplying out the brackets. 2 sine theta times 5 cos theta gives us 10 sine theta cos theta. 2 cos theta times 5 cos theta gives us 10 cos squared theta. Next up on the other side, we've got minus 5 sine theta times 2 cos theta, which gives us minus 10 sine theta cos theta. And finally on the top here, we've got minus 5 sine theta times by minus 2 sine theta, which gives us positive 10 sine squared theta. And that's all over 2 sine theta plus 2 cos squared theta. At this point, I wouldn't multiply out that squared bracket yet. Sometimes things will cancel, sometimes we'll have no choice but to multiply it out. But at the minute, you can see that the 10 sine theta cos theta will cancel with the minus 10 sine theta cos theta, leaving us just with 10 cos squared theta plus 10 sine squared theta on the top. Well, something should look familiar here, okay? We should remember the identity and have it ingrained in our memory that sine squared theta plus cos squared theta equals 1. So I've cleared a little space here for us to carry on with this question. So let's look at what we've got left of dy d theta. We could factorise out the 10 and say we've got 10 brackets sine squared theta plus cos squared theta all over 2 sine theta plus 2 cos theta all squared. Well, looking at the identity above, we know sine squared theta plus cos squared theta is 1. So this simplifies down to just 10 over 2 sine theta plus 2 cos theta squared. Now, this is where we probably do need to write it as double brackets and then multiply it out. Because if there was going to be any cancellation, we would have seen that by now. So let us have a go at multiplying out those double brackets. So we've still got 10 on the top, and now that's going to be over. Firstly, we'll do 2 sine theta times 2 sine theta. So that's over 4 sine squared theta. And then we can do 2 sine theta times by 2 cos theta. That is going to give us 4 sine theta cos theta. Next up, let's have a go at doing 2 cos theta times by 2 sine theta. That gives us 4 sine theta cos theta. And finally there we have 2 cos theta times 2 cos theta, which is going to give us 4 cos squared theta. So there we go, looking nice, looking like it's got a lot of stuff going on there. Let's simplify this a bit. So here we've got 10 over 4 sine squared theta, and I'm going to write next to that plus 4 cos squared theta. And then I've got plus 8 sine theta cos theta, because those two that I've underlined are like terms. Well, I can see that I can use my sine squared plus cos squared equals 1 identity again here, because I've got 4 of those. So that's going to simplify just to 4. Okay, so we've got 10 over 4 plus 8 sine theta cos theta at the minute. Now there's another identity that we should recognise here. We should know that sine 2 theta equals 2 sine theta cos theta. And therefore we should recognise that if we have 8 sine theta cos theta, we've actually got 4 of those sine 2 thetas. And so we can make this little substitution here. And we end up having now 10 over 4 plus 4 sine 2 theta. And we've nearly finished this now, except that we want a to be a rational constant to be found. So if we factorise out that 4 on the bottom here, we get it in the form that we need. which has 1 plus sine 2 theta on the bottom. And therefore we can see that A in this case must be 10 over 4, or that simplifies to 5 over 2. And that is what A is here, and we have rewritten it in the way desired in the form A over 1 plus sine 2 theta. A curve is defined by two parametric equations, x equals 2 cos 2 theta and y equals 4 plus cos theta. Here we're asked to find dy dx in terms of k sec theta, where k is a constant to be found. So for this we need to remember that in parametric equations, dy dx is equal to dy d theta times by d theta dx. The reasoning for that is this is the chain rule, essentially those d thetas cancel, and d theta dx is coming from the reciprocal of dx d theta. So what we need to do to be able to solve this then is to differentiate x with respect to theta and to differentiate y with respect to theta. So in this case here, we've got 2 cos 2 theta. We know cos differentiates to negative sine, but because we have a 2 theta there as well, we have to do the chain rule. Now when using the chain rule, you look at the bit that's a little bit non-standard from the identity that you've learnt, and you differentiate that. Here I can see that 2 theta differentiates just to make 2, and we multiply through by that factor. And that is why here we don't just have minus 2 sine 2 theta as our answer. What we actually have is minus 4 sine 2 theta. And so there we have it. So now we need to do exactly the same for y. Y equals 4 plus cos theta. Now differentiating that, we should know 4 just goes away when we differentiate it because it's a constant. And then we've got cos theta, which we know differentiates to minus sine theta. So there we've got it. We've got the two bits we need to be able to differentiate this. dy dx is equal to dy d theta. So that is minus sine theta. And then we times it by the reciprocal of dx d theta. So we're going to times it by 1 over minus 4 sine 2 theta. And now we're told that we need to get this in terms of k sec theta. It's clearly not there yet. However, I can see that there's some ways that I can simplify this. First things first, let's just tidy this up. I can see that there's a minus on the top and the bottom, so it just becomes positive, and I'm left with sine theta over 4 sine 2 theta. Now let's think about this. I know an identity for sine 2 theta, and you should too. If you don't know it, then make sure you learn it. So sine 2 theta equals 2 sine theta cos theta. So I'm going to make that substitution in here now. So I've got dy dx equals sine theta over 4 times 2 sine theta cos theta. Here I can see that I can actually cancel out the sine thetas now. And that ends up giving me 1 over 8 cos theta. But there's another identity that we need to know here to finish this off. It's very important that we know that sec theta is equal to 1 over cos theta. Now for that reason here, because I've got 1 over cos theta, I can rewrite this then as 1/8 sec theta. And so that is what k is. K is 1/8. That is the constant that we needed to find. So dy dx equals 1/8 sec theta. So now we're asked to find the integral of y with respect to x between 1 and 0, giving our answer in simplified surd form. So we need to know that when we have parametric equations, the integral of y with respect to x equals the integral of y dx d theta. And essentially this is another form of chain rule. We can see that those d thetas effectively cancel out. However, they're going to very powerfully enable us to rewrite this in terms of theta. So from the earlier part of the question, we know that y equals 4 plus cos theta, and we worked out that dx d theta was equal to minus 4 sine 2 theta. For that reason now, we can make the substitutions here. We can say that the integral of y dx equals 4 plus cos theta times by minus 4 sine 2 theta. and that is with a d theta on the end there. So first thing that I would do is I would multiply out my brackets now. I can see here if I do 4 times by minus 4 sine 2 theta, I get minus 16 sine 2 theta. And then if I do cos theta times by minus 4 sine 2 theta, I'm just left with minus 4 sine 2 theta cos theta. And then I'm going to put d theta on the end there. So I need to integrate both of these terms. I can see here that I also have a little identity. I can see sine 2 theta pops up in both of these. I know off by heart that sine 2 theta equals 2 sine theta cos theta. Now, the first term, this minus 16 2 theta, I'm not going to make that substitution for, because I can integrate that quite easily as it is. However, this second term, I am going to make that substitution for. I can see that if I substitute in place of sine 2 theta, 2 sine theta cos theta, I'm left with minus 8 sine theta cos squared theta. So this is now a set of terms, 2 terms, that I can integrate. Now, before we get to integrating those though, we need to tackle the limits in this, because those limits are x values. We need to change them so that we have them now in terms of these theta values. So we know that x equals 2 cos 2 theta from the earlier part of the question. And so when x equals 1, we can say that we have 2 cos 2 theta is equal to 1. Now, rearranging that, we can say that cos 2 theta equals 1 over 2. And if we keep our calculator in radians for this question, we're going to find that 2 theta equals pi over 3. And therefore, our last little easy bit of rearranging, we find that theta equals pi over 6, just by dividing through by 2. So now we've got x equals 0. So now we're going to say 0 equals 2 cos 2 theta, and therefore cos 2 theta equals 0. If we do the inverse cos of both sides in radians, we get that 2 theta equals pi over 2, and therefore finishing that up, we get that theta equals pi over 4. So there we have it. We have our 2 limits now. So our upper limit we're going to put as pi over 6 now, and on the bottom we're going to put pi over 4. So now we're ready to do our integration. We've got the limits we need. We've written everything in terms of d theta. We're good to go now, okay? So we've got 2 different terms and we're going to integrate those separately. Now, the first of these 2 terms is, of course, minus 16 sine 2 theta. Now, we should recognise that that is just an adaptation of your normal sine theta. And we know how to integrate sine theta, don't we? We know that sine theta goes to negative cos. So in this case here, with this being that 2 theta, we need to apply our chain rule. So as well as changing the sign to negative cos, we also need to differentiate that 2 theta bit and divide through by that differential. So in this case, you can see I have changed the negative to a positive because the sign went to negative cos and 2 minuses make a plus. And I've divided through by 2 because it was 2 theta, so I had to apply the chain rule. So I differentiated that slightly weirder bit compared to the normal identity you've learnt. And then I divide through by that number, and then I'm left with this 16 cos 2 theta over 2. Next up, we need to integrate minus 8 sine theta cos squared theta. Now with this, some people can use the inspection method or the reverse chain rule, and they would recognise that this integrates to make plus 8/3 cos cubed theta. Now, I think that method's a bit of a stretch, to be honest, and I think a lot of students really get confused with that one. If you're one of the lucky ones that love it, then great, well done you, keep doing it that way, okay? If you're someone that gets a little bit confused on this, then I would recommend that if you're ever in doubt, use the substitution method. That method is going to get you out of a lot of scrapes. It works majority of the time with integration. And so I'm going to quickly go off to the side here and show you how I would do it using substitution. So I would say, so I've got minus 8 sine theta cos squared theta, d theta. I want to integrate that. Let's say that u equals cos theta. And generally with substitution, I choose the bit in the slightly more complicated bit. So I've got cos squared, so I'm going to say, let's make u cos. Now that I've got that, let's work out what du d theta is. If I differentiate cos, I know that I get negative sine. So du d theta equals minus sine theta. Now if I rearrange that then to get d theta as the subject, I end up getting that d theta is equal to du over minus sine theta. So if I put that now into our equation here, I end up finding that I've got minus 8 sine theta. Cos squared theta will just be u squared. D theta is going to be du over minus sine theta. Notice here I now get this cancellation of the minuses and of the sine. And all that I'm left with here now is going to be 8u squared. And of course, we do know how to integrate 8u squared. It's one of the easy ones, isn't it? All that we need to do this now is going to be add 1 to the power and divide by that power. And that ends up giving us 8u cubed over 3. And finally, of course, we said that u was cos. So here we've got 8 cos theta cubed over 3. And that is exactly what we've got here that we could have got through the inspection method. And yeah, that's a very quick method, but either you get it or you don't. And at this point, I think it's good to have a good backup method. And like I say, the substitution method is a great backup method. So we've got this now. All that we need to do is to put our limits in. So we've got the limits here from pi over 6 to pi over 4. So now let's substitute those in. Here we're going to get 16 cos 2 times pi over 6 all over 2, and then plus 8 thirds of cos cubed pi over 6. And then we're going to subtract from that 16 cos 2 times pi over 4, and then all over 2. And then plus 8 over 3 cos pi over 4 cubed. And now that we've got that, we can put this into the calculator. So starting with this first term here, when I put this into the calculator, I get 4. When I put this term in, I get root 3. And then I subtract. This goes to 0. And this is 2 root 2 over 3. So our final answer here is 4 plus root 3 minus 2 root 2 over 3. And that is our integral. Here we're asked to find our Cartesian equation for the curve in the form y equals fx. So with this, let's remind ourselves x equals 2 cos 2 theta and y equals 4 plus cos theta. Now the trick for finding Cartesian equations when trigonometry is involved is ask yourself, can I think of an identity that has both this cos 2 theta in it and cos theta in it? And of course we do, don't we? We should know off by heart double angle formula that states that cos 2 theta equals 2 cos squared theta minus 1. And what we need to do is rearrange these equations really and substitute them in. So here we know that x equals 2 times by 2 cos squared theta minus 1. And that is just directly making that substitution with that identity there. By doing that now, if we multiply out those brackets, we get x equals 4 cos squared theta minus 2. If we go over now though to the y equation, so y equals 4 plus cos theta. Therefore we can say that cos theta is y minus 4, and so cos squared theta is y minus 4 squared. Now this we can just make a direct substitution for here. We can say that x equals 4 times by y minus 4 squared, and then minus the 2. Now in this question, we do have a Cartesian equation now. It's just in terms of x and y. However, we want it in the form y equals f of x. So that means we need to rearrange this bit by bit to get the y on its own. So here we could add the 2 onto the other side and get 4y minus 4 squared equals x plus 2. Now we could divide through by the 4 and get y minus 4 squared equals x plus 2 over 4. Now we could square root this to get the y minus 4 on its own. So we've got y minus 4 equals the square root of x plus 2 over 4. And then finally, we can just add on that 4. So here we've got y equals the square root of x plus 2 over 4, and then plus 4 outside of that square root. So that is it. That is our Cartesian equation. What we can do here is we could write that in a slightly different format. We would still be correct to call this y equals the square root of x over 4 plus a half, and then outside of the square root a plus 4 on the end. They both mean the exact same thing, so there we go. Main moral of the story with this question is if you're ever asked to find Cartesian equation for a curve and there's trigonometry involved, just ask yourself, can I think of an identity that has all of these causes or tans or whatever the question's got in it? And write down that identity and then substitute what you know into that identity and then rearrange to get it in the form desired. So there we have it. I hope that makes a lot of sense. A ball is kicked into the air from the ground by a footballer. The moment the ball leaves the footballer's foot, it moves with a speed of u at an angle alpha to the horizontal. The football lands on the ground 20 metres away from the footballer. The footballer is modelled as a particle moving freely under gravity g, and we're asked to show that 20 tan alpha minus 200g over u squared sec squared alpha equals 0. Now, at first glance here, that equation, it tells us nothing. It's there to confuse us, essentially. And where people go wrong with these types of questions is they place too much focus on what you're being asked to show, instead of the actual problem. What we should do when we enter into this question is we should understand that this is a projectiles question. And when we have a projectiles question, we essentially have to use SUVAT in both the horizontal and the vertical planes. So we need to divide this problem up into thinking about what's happening vertically and horizontally. Now, as this is a projectiles question, generally speaking, that's the extent of it. So although this is a show that, and it looks quite intimidating, all we need to do is recognise the topic and then just crack on doing exactly what we normally would in these questions. So what I'm going to do here is I'm going to resolve it horizontally and vertically. I'm going to use my SUVAT equations perhaps to calculate some things, and then I'm going to go from there. Okay, so let's get started and see how this unfolds. And what we should find is that eventually it becomes clear how this show that will arise. So let's get started by resolving this speed. The horizontal component is going to be u cos alpha. The reason for this is because, of course, that horizontal component is the adjacent of this triangle and u is the hypotenuse, making cos. And we use the same idea to work out that that vertical component is u sine alpha. That side of that triangle is the opposite side, and of course we know that u is the hypotenuse, so we get u sine alpha. So now let's have a think about what other information was given to us. We're told that the football lands on the ground 20 metres away from the footballer. So we know that that horizontal distance is 20 metres. We also know in the vertical direction that the acceleration is going to be due to gravity. So the acceleration downwards is equal to g. And that's all the information that we know at the minute. Let's have a go then at resolving horizontally to start with. So we've already said that u equals u cos alpha. A is equal to 0 in the horizontal direction. that's always the case. We're always assuming that air resistance is equal to 0, and of course gravity isn't acting in that direction either. So in the horizontal direction, we always say that A is equal to 0. Then we know S is equal to 20. The time, however, that takes, we don't know. Now, time is an important parameter in these questions because time is the one parameter that is true for both the horizontal and the vertical. To get from the beginning to the end takes the same time whether you look at it from a horizontal or a vertical perspective. So for that reason, let's calculate the time because that can carry over into the vertical. So S equals ut plus a half at squared. Because A is equal to 0, we can just say that S equals ut. If we substitute, therefore, what we have into this, then we get 20 for S equals u cos alpha times by t. So here we've constructed a formula and we've gone as far as we can really with the horizontal component. So now let's have a look at the vertical region. So vertically speaking, we said that u equals u sine alpha. A is going to be equal to minus g because initially we're going upwards, aren't we? Okay, so we're going against gravity, making it negative g. Now if we look at the beginning and the end, see in that vertical direction, we end at the same point that we started, vertically speaking. So S is equal to 0, the displacement is 0, and time is just equal to t, like it was horizontally. So we can do the same thing here, and we can use the same Suvat equation. We can say that S equals ut plus a half at squared. Now substituting everything in here, we get 0 equals u sine alpha t plus a half times minus g times by t squared. So there I end up getting 0 equals u sine alpha t minus g over 2 t squared. So now it's reaching a point where we've kind of reached a dead end almost. We can't do anything more in terms of the vertical or the horizontal. However, we have got two equations now. What we could do is we could rearrange one of these, perhaps to get t as the subject. That would make sense because, see this equation here, it doesn't have t in it. And then eliminate it from the other equation. So here I've rearranged to say that t equals 20 over u cos alpha. If I substitute it into this vertical equation, I've eliminated t, and I'm making it look a lot more like this show that. So here I get 0 equals u sine alpha times 20 over u cos alpha minus g over 2 times by 20 over u cos alpha all squared. So now all we need to do is do some simplification. I can see it's starting to look how we want it to. I'm starting to see some similarities here. So let's clear a little bit of space here so that we can do some simplifying. So first things first, let's just tidy this up a bit. So we've got 0 equals, and I'm going to rewrite this first term as 20u sine alpha over u cos alpha. So it just looks a little bit nicer. And then we've got minus g over 2 times by 400 over u squared cos squared alpha. So we've simplified that, and let's do a bit more now, okay? I can see that I can cancel out the u's in this first term. There's a u on the top and the bottom. And on the second term, I can do 400 divided by 2, leaving me with 200 on the top there. So let's write this a bit simpler again. So here I've got 0 equals 20 sine alpha over cos alpha minus 200g over u squared cos squared alpha. So that's looking a lot nicer now, and I can see again a lot of similarities with what we need to show. But let's remind ourselves of a couple of identities here from pure maths, but they still come up in mechanics. We know that tan alpha equals sine alpha over cos alpha. So we can make that substitution first. We can say we now have 0 equals 20 tan alpha. And then we have got 1 over cos alpha equals sec alpha. And that's going to be handy over in this second term here, where essentially we have 1 over cos squared alpha. So if 1 over cos alpha equals sec alpha, then 1 over cos squared alpha will equal sec squared alpha. So we can rewrite that second term as minus 200g over u squared sec squared alpha. And now we have got exactly what we needed to show. So we've done it. And see how actually we didn't use that shape that until right at the end when it was tidying it up and making it look how they wanted it to. Essentially, all that we needed to do prior to that was just use our projectiles knowledge and do the CVET that we would with any projectiles question. So even if you have no idea where you're going with it, you can still just go through the motions and you'll still have majority of the marks, even if you can't finish it off. It is given that cos alpha equals 3/5. Find the initial speed of the ball when it is kicked by the footballer. Well, we have got the equation from part A, haven't we? And just in case you couldn't do part A, know that whenever you have a show that, chances are you can use that show that in later parts, even if you couldn't work out the first part. So I'm just going to write down that equation that they gave us. 20 tan alpha minus 200g over u squared sec squared alpha equals 0. And here we're asked to find the initial speed of the ball, which is u. We're told that cos alpha equals 3/5. So if we draw a little right angle triangle here, we can remember that cos is adjacent over hypotenuse. So we've got 3 in the place of the adjacent and 5 in the place of the hypotenuse. Using Pythagoras, or just knowing that this is one of our magic triangles, we can say that the opposite then is 4. Therefore, tan alpha, which is the opposite over the adjacent, is 4/3. And sec alpha, which is the reciprocal of cos alpha, will be 1/3/5, which is equal to 5/3. So now we know what tan alpha is and we know what sec alpha is, we can substitute these now directly into our equation. So you've got 20 times pi, and in place of tan alpha we're putting 4/3, minus 200g over u squared times by sec squared alpha. Well, if sec alpha is 5/3, we just need to square that, and then we put equal to 0. Let's tidy this up then. 20 times 4 is 80, and then over 3. And we've got minus 200g over u squared times by 5/3 squared. Well, 5/3 squared gives us 25/9. So if we multiply that through by 200g over u squared, you get 5000g over 9u squared. So here we've got 80/3 minus 5000g over 9u squared equals 0. Now rearranging that, we can say 80/3 equals 500g over 9u squared. We can flip that upside down to get the u squared on the top, which makes our lives a lot easier. And then rearranging that to get u as the subject, we get that u equals the square root of 3 times 5000g over 80 times by 9. So this ends up giving us u equals 14.29 meters per second. Now in part C, we're asked to calculate the maximum height reached by the football. So if we think about this vertical plane here, we need to remember that vertically, when it reaches that maximum height, the velocity is equal to 0. So we know that u in the vertical plane is equal to u sine alpha. We're saying now that v equals 0 at that maximum height. Because we're moving upwards away from gravity, a is equal to minus g, and s is what we need to find. So we can work out a number for u, because if cos alpha equals 3/5, using our triangle and the fact that sine alpha is equal to opposite over hypotenuse, we find sine alpha is 4/5. And we worked out in part B here that u is equal to 14.29. So u sine alpha equals 14.29 times 4/5. If we now find a CVET equation that fits all of these, u, v, a, and s, we know that we need to use b squared equals u squared plus 2as. So let's substitute in some numbers here. So here we've got 0 squared equals 14.29 times 4/5 squared plus 2 times minus 9.8 times s. Now, simply by rearranging this, we end up finding that s equals 6.67 meters. And that's it. Finally here, we're asked to state one assumption made in this model. And so we have assumed, as we do in all projectiles questions, that there is no air resistance. We could also say that there's no wind. And that is why we could make a lot of the assumptions in this question when talking about this horizontal plane having no acceleration. So, good work. I hope that that's nice and clear now. Every projectiles question is the same as the last, so if you can ace this method, you'll be fine on any projectiles question. A particle A moves with a velocity v meters per second at a time t. We know that v equals t squared plus 2ti plus minus 8t plus 5j, where I and j are unit vectors due east and north respectively. Here we're asked to find the magnitude of the acceleration of the particle when t equals 5 seconds. So in order to answer this, we need to understand that the acceleration is the differential of velocity with respect to time. So that means that we need to differentiate v to find the vector of acceleration. So in this case, dv dt, taking it one thing at a time, the 2 squared will differentiate to give 2t, and the 2t differentiates to give us 2. Now those are the I components, so we put brackets around those and then an I on the outside. Now for the j components. Minus 8t differentiates just to minus 8, and the 5 just goes away. So here we're left with minus 8j. Don't forget the I and the j components. Here though, we're being asked specifically for the magnitude of the acceleration when t equals 5 seconds. So let's make that substitution of t equals 5 seconds. So a is equal to 2 times 5 plus 2, and then that's the I component, and then minus 8j. That simplifies down to give us 12i minus 8j. However, we're not there yet. They want the magnitude. And to find the magnitude of any vector, we need to essentially do Pythagoras' theorem. So here the magnitude of A is going to equal the square root of 12 squared plus minus 8 squared. Don't forget the brackets. That ends up giving us the square root of 208, which, if we put that into the calculator, gives us 14.42 meters per second. And that is the magnitude of the acceleration of the particle when t equals 2 seconds. So now we're asked to find the displacement between t equals 1 seconds and t equals 4 seconds. Now, in order to answer this, we need to understand that the displacement s is the integral of the velocity with respect to time. So this time round, we now need to integrate velocity to find the displacement. So let's remind ourselves of what v is. So to find s, we need to integrate t squared plus 2ti plus minus 8t plus 5j, and that's with respect to time. So let's do these one at a time then. T squared will become t cubed over 3, because remember, when we integrate polynomials, we add 1 to the power and divide by that new power. 2t becomes 2t squared over 2. Those are our I components of this vector. Minus 8t becomes minus 8t squared over 2. And the plus 5 becomes plus 5t, and those are the j components. Now, because we wanted the displacement between 1 second and 4 seconds, actually we wanted to integrate between the limits of 4 and 1. So that means now we've integrated, we need to substitute in 4 to start off with, and then subtract it with the 1 substituted in. So starting with the 4, we get 4 cubed over 3, plus 2 times 4 squared over 2, and then those are the I components. And then plus minus 8 times by 4 squared over 2, plus 5 times 4, and then those are the j components. And from that we need to subtract the same thing but with 1 substituted in place of t. So this is going to be 1 cubed over 3, plus 2 times 1 squared over 2, those are the I components, and then plus minus 8 times 1 squared over 2, plus 5 times 1, and those are our j components. So, bit of a mouthful that. Very easy to miss something along the way and make a mistake as well. But now we need to simplify that. So I'm going to do these one at a time. I'm not going to rush it, because rushing is where mistakes come in. Just popping this bit that I've highlighted in green into the calculator ends up giving me 112 over 3i. So I'm just doing that first. I'm not rushing this. Next up, let's do the j component. So there I end up putting that into the calculator and getting minus 44j. So that's that bit done now. Then I'm going to subtract this other component, okay? So I'm subtracting 4/3 I. And then working out this last component. And don't forget that both of these are actually subtracted from the previous bit, which is why I put brackets in now, okay? Just so that we don't forget that. So this final part just gives us 1, so we just have j as that last component. So to finish up, to get this displacement, we need to group up the I terms and the j terms. So 112 over 3 minus 4/3 I gives me 36I. And minus 44j minus j gives me minus 45j. So there we have it. That is the displacement between t equals 1 and t equals 4 seconds. So now for the last part of this question. We're asked to find the times the particle is moving in the northwest direction. So in order to answer this, let's first remind ourselves of what that means on a grid, okay? So if we're going the northwest direction, we're going in this direction here. And we need to know that if we are going in the northwest direction, we are moving parallel to the vector minus I plus j, which means some multiple of minus I plus j is your movement, is your velocity. So as we know that velocity was equal to t squared plus 2ti plus minus 8t plus 5j, we can now form an equation to help us solve this and find these times, okay? So let's clear a little bit of space so that we can do this. So to make this clearer, I'm going to rewrite this velocity as a column vector. Now you don't have to do this, but I just like how it visually looks. It feels clearer to me. So I'm going to put the t squared plus 2t on the top because that's the I component, and the j component of minus 8t plus 5 I'm putting on the bottom. So we said that the northwest is parallel to minus I plus j. So it's some constant times by this minus I plus j. So I can say that the I component could be minus k, some constant, and the j component could be just k. They have to be the same factor though, in order for it to be parallel. So that's what I've said here, okay? Now I can write some equalities with this. I can say that k equals minus 8t plus 5, and therefore I can also say that minus k equals t squared plus 2t. Now this enables us to form a little equation, doesn't it? Because if t squared plus 2t equals minus k, and we know k is minus 8t plus 5, we can make that substitution. Now doing that, and then multiplying out this bracket essentially, we get t squared plus 2t equals 8t minus 5. So now this should look like a quadratic equation to you. And we all know how to solve quadratic equations using one method or another. So shifting everything over to one side so that we can solve this, I end up getting t squared minus 6t plus 5 equals 0. I can factorise this. I can see this is going to be t minus 5, t minus 1, which equals 0. And now solving this using these brackets, I get that t equals 5 seconds and t equals 1 second. And those are the times that the particle is moving in the northwest direction. So that's how we do a question like that. Be aware they could say in the northerly direction, the westerly direction, east, southeast, all these permutations, okay? We're going to use that same idea. Remember that I will represent the east direction, minus I would be the west direction, the north direction would be j, and the south would be minus j. So if something's moving parallel to that, it could be moving some constant amount times by those. So I hope that that was clear, and I hope that you can now apply this in a similar question if it comes up in your exam. Two balls A and B are connected by a light and extensible string. Ball A has a mass of 2.3 kilograms and ball B has a mass of 2.7 kilograms. Ball A is held at rest on the surface of a rough horizontal table. The string connecting A and B is passed over a smooth, light pulley. We're told that ball B hangs freely at rest vertically below the pulley. At time t equals 0, ball A is released and it moves with an acceleration of A, and ball B hits the ground at 0.7 seconds. Here we're asked to calculate the acceleration of ball A. Now, let's start off by labelling everything here. This is the most important thing in any question. We know that the mass of ball A is 2.3 kilograms, so its weight acting down is 2.3 g, and the mass of B is 2.7, so the weight is 2.7 g. Next up, we can draw on the tensions, okay? So the tension on A is pulling it to the right, and the tension on B is pulling it upwards. Now we know that it has an acceleration of A. Let's draw those arrows on showing the direction in which it will actually be accelerating. So another piece of information that's really important here is that we have a rough table. That means that A is going to have a frictional force opposing its motion, which will go to the left. A is also sitting on a table, so it will also have a reaction force acting upwards. Now that's everything that we can really label on. Let's have a think about how we can calculate the acceleration of ball A. Well, the first thing to realise is because A and B are connected by this light inextensible string, the acceleration of A is the same as the acceleration of B. So that initial acceleration of ball A is corresponding to the point where B is falling to the ground. Now the distance that B falls to the ground is s equals 0.4 metres. We know that they were both hanging from rest, so u is equal to 0 metres per second. The time it took for ball B to hit the ground was 0.7 seconds. And of course, we're being asked to find the acceleration. We've got enough things now to put into a SUVAT equation to find out the acceleration of both of these balls. So s equals ut plus a half at squared is the most suitable one in this case. Let's substitute everything in. So here I've got 0.4 equals 0 times by 0.7 plus a half times a times 0.7 squared. Simplify that a bit here. That gives us 0.4 equals 0 times 0.7 is just 0. And a half times by a times by 0.7 squared gives me 0.245a. So if I rearrange this now, I will get the acceleration. And that is 0.4 over 0.245, which gives me an acceleration of both the balls, A and B, of 1.63 metres per second squared. And so there we have answered it. Now in questions like this that involve pulleys, generally speaking, you're going to use SUVAT and or F equals MA. Those are, realistically speaking, the only two ideas that you're going to need to use in these questions. And do you know what? This is one of the things that's quite good about mechanics. There's not many different things that you learn. And so they're just going to get used repeatedly in these questions. Okay, so we've just used some SUVAT. I'm guessing that probably we're going to have to use some F equals MA for whatever the next question is. Let's have a look. So here we're asked to calculate the tension T in the string. So the way that I would answer this is I would divide this up into two different systems, okay? I've got the system belonging to ball B, let's call it system 1, and I've got the system belonging to ball A, let's call that one 2. And we don't need to use them both at one time, okay? We can take them one at a time. And in this case, I am going to use system 1, at least to start off and see how we get on. So I'm going to use the equation F equals ma. So F is the resultant force, and as we're moving downwards, that resultant force will be 2.7 g, which is the force acting downwards. And then we're going to subtract the force in the opposite direction. So we're going to subtract T from that because it opposes and makes that resultant force smaller. And that's equal to ma, which for B is equal to 2.7 times A. So we worked out, didn't we, that A is equal to 1.63 metres per second squared. So let's substitute that into here. So now I have 2.7g minus t equals 2.7 times 1.63. So if I rearrange that now, I get t equals 2.7g minus 2.7 times by 1.63. Now if I put that into the calculator, I get that t equals 22.059 newtons. And there we have it, we've got the tension in the string. So for the last part of this question, we're now asked to find the coefficient of friction mu between the table and ball A. So in this case, I would say we need to look at system 2 because that's the one that includes the friction. Again, F equals ma, and this time it's moving to the right. So the resultant force will be equal to T minus friction. And that's equal to ma, which in this case is 2.3 times A. Now, I know that the tension is 22.059. And I also know that A equals 1.63. Now I can substitute both of these in to then rearrange and find out what friction is. Rearranging the equation, I can see that friction is going to be equal to T minus 2.3A. And so substituting these numbers in, I find friction equals 22.059 minus 2.3 times 1.63. Tapping that into the calculator, I find that the frictional force is equal to 18.31 newtons. However, that isn't what they wanted, is it? The question is asking for the coefficient of friction. We know friction equals mu times R, and the reaction force is the force perpendicular to the table, so acting upwards on this force A. Now, it's not accelerating up or down or anything, is it? It's just sitting on this table. So for that reason, we can look at the upward and downward forces acting on A and say that they must be balanced. Therefore, we can say that R is equal to 2.3g. So now then, we can say that friction is equal to 2.3g times by mu. And so if we substitute this in place of the friction, we can solve it to find out what mu is. So mu times 2.3g equals 18.31. If I get the mu all on its own here, I find that mu equals 18.31 over 2.3g. And if I put that into the calculator, I end up finding that mu equals 0.81. And that's our answer. That is the coefficient of friction. A good tip to know that when we're trying to find coefficient of frictions is remember it always has to be a number between 0 and 1. If you ever got an answer bigger than 1 or less than 0, then you know that something has gone wrong and you know that you need to go back and just double check your working to see if you've made a really obvious mistake. A ladder of mass of 5 kilograms and length 10A is placed against a smooth vertical wall onto rough horizontal ground. Now, if it has rough ground, then we know that there's a frictional force at X. So I'm just going to add that on here, just to make sure that I'm not missing anything as I go. And that force of friction is going to be towards the wall. Imagine you've got a ladder leaning, it's going to be scraping forwards and the friction will be opposing that. The coefficient of friction between the ladder and the ground is 0.4, so we know that mu equals 0.4. We're told that the angle between the ladder and the ground is alpha. Great, that's already labelled. And we're told that a person of weight 70 kilograms stands on the ladder at point Y, where x to z to y to z is in a 3:1 ratio. Well, let's draw on the weight of that man then at Y. So we're going to have a downwards force of 70g, and we know that x to y to z is in a 3:1 ratio. Well, the length of x to z is 10a, so if we split that into a 3:1 ratio, we end up getting 7.5a and 2.5a. So let's label that onto our diagram again. See how I'm labelling as I go, rather than even waiting to read the question. Let's make sure we get that information down. The diagram is vital in mechanics. So the last thing that we need to add is the fact that the ladder has a mass of 5 kilograms. Now, unless they say otherwise, we assume that this ladder is uniform, which means that the mass is evenly distributed. Therefore, we're going to have a downwards force of the weight equal to 5g, and that is a distance of 5a from x, and also a distance of 5a to z. So we've got two final forces we need to add in here. We've got the reaction force at X, which acts upwards, which we call Rx. And we've also got the reaction force at Z, which let's call it Rz. And that is again perpendicular to the surface it's acting on. So it is acting this time to the left-hand side. Notice how we didn't have any friction at Z, and that's because it told us that this is a smooth vertical wall, and therefore there just won't be any friction. So we have fully labelled our diagram. Now in mechanics, in any question like this, or to be honest, most questions in mechanics, I wouldn't even start proceeding with the question until I have a fully labelled diagram. You cannot underestimate the importance of these labelled diagrams. They will ensure that you can visualise the situation, see what's going on, and it will stop you making mistakes. So here we're told in this question that given that the ladder is modelled as a uniform rod and is under limiting equilibrium, find the angle alpha. Well, when something's in equilibrium, we can say that the upwards forces equal the downwards forces, the forces to the left equal the forces to the right, and also the clockwise moments equal the anti-clockwise moments. Let's first resolve the up and down forces. As you can see here, I've highlighted in green all of those up and down forces. Here, let's say that the upward forces, so in this case Rx, are equal to the sum of the downwards forces. In this case, that is 5g plus 70g. Using that fact, we can see then that Rx, that reaction force at X, is equal to 75g. Now, let's do the exact same thing now, but resolving the left-hand forces and the right-hand forces. So, doing that horizontally now, we find that Fr is equal to Rz. Those are the only two forces in that horizontal plane. And so Fr is equal to Rz. So we also know, though, that generally speaking in mechanics, the frictional force is equal to mu times by R. So in this case, Fr is equal to mu Rx. So we can make that substitution here. And we can say mu Rx is equal to Rz. We've just said, haven't we, that Rx is equal to 75g, and mu, we're told actually here, is equal to 0.4. So we can say 75g times 0.4 is equal to Rz, and therefore Rz is equal to 30g. So bit by bit, we're working out what all these forces are. All of these unknowns are becoming known. So now we've done all the resolving of forces. Let's look at the moments, okay? Let's take moments about X in this case, and let's say that the clockwise moments are equal to the anti-clockwise moments, due to the fact that we are currently in equilibrium. And let's remind ourselves of how we calculate moments. So moments are calculated by saying force times by perpendicular distance from pivot. That is a critical point in these questions, and it will make the difference between you getting your marks. So as we said, in equilibrium, the clockwise moments equal the anti-clockwise moments. Let's get started then by working out these moments. Let's start off with this force here, the weight of the ladder. Okay, so let's look at the moment caused by the weight of that ladder. We should see that this weight causes a clockwise moment around the pivot X. We know its force, and then we times by the perpendicular distance from the pivot. Now the force we can see is 5g. However, this distance of 5a that it currently is from the pivot, that is not perpendicular. Okay, we need to always have the force and that distance at right angles to each other. And we can resolve either the force or that distance, to be perfectly honest, so long as the two things you end up with are at right angles. So what we actually need is this distance here. And we can work this out by simply doing a bit of resolving, okay? By using Pythagoras' theorem, we can see that that's the adjacent of this right-angled triangle. And so we end up with 5g times by 5a cos alpha. That is that perpendicular distance between the force and that pivot. So I can see here I have another clockwise moment, and that is due to the weight of that man. So force times perpendicular distance again. I can see that I have 70g for my force, The distance would be 7.5a, but that isn't the perpendicular distance. Again, we need to resolve this. In this case, using the fact it's a right-angled triangle again, I can see that that perpendicular distance between the distance and the force is going to be 7.5a cos alpha. So there are both of my clockwise moments. Now I need to say that that's equal to my anti-clockwise moments. And here I can only see one, and that is going to be the moment caused by the force Rz. Now the perpendicular distance in this case is going to be this downward force from Rz to x. Now in this case that's the opposite of a right-angled triangle, and so I'm going to have here the distance is actually 10a, because that's the length of the whole ladder, times by sine alpha to get that vertical component. So my anti-clockwise moment is Rz times 10a cos alpha. So I have now got that full equation that shows my moments. I can say that my clockwise moments are equal to my anti-clockwise moments, and therefore I've got here 5g times 5a cos alpha plus 70g times 7.5a cos alpha equals Rz times 10a sine alpha. And so let's now do a little bit of rearranging to eventually end up finding out what alpha is. So let's start with a clear space now. Let's recap everything that we now know. We know that Rx equals 75g. We know that Rz is equal to 30g. And we also know this big equation that we just got. If we simplify it, it becomes 25ag cos alpha plus 70 times 7.5 gives us 525 ag cos alpha. And then that is, of course, equal to our anti-clockwise moments. And that is equal to Rz times by 10a sine alpha. Well, let's substitute in this value of Rz and let's tidy up the clockwise moments here. 25 ag cos alpha plus 525 ag cos alpha gives us 550 ag cos alpha. Substituting in place of Rz, 30g, we get 30g times 10a sine alpha. Let's simplify this again. Here I've got 550 ag cos alpha is equal to 300 ag sine alpha. Here I can actually see that I can cancel out the a's and the g's because they pop up on both sides here. And finally, to get alpha, I'm going to have to use a trigonometric identity. I'm going to have to use the fact that I know that sine alpha over cos alpha is equal to tan alpha. So if I rearrange this to that effect, I end up with 550 over 300 equals sine alpha over cos alpha, which equals tan alpha. And so therefore, as tan alpha equals 550 over 300, we can therefore rearrange that to say that alpha is going to be equal to 61.4 degrees. And that is the answer that they wanted. A box of mass 2 kilograms is placed on a rough plane at point X. So as we've just read that, let's just fill that in on the diagram, okay? Let's do a downward force of 2g, because that is the weight corresponding to a mass of 2 kilograms. And as we know, we have a rough plane, and of course they've just put this box onto this plane and gravity will be pulling it down. We know that we have a frictional force acting upwards, up this plane. So I've written this on as well. So now we're told that the coefficient of friction between the plane and the box is 0.7. So let's make a little note that states that mu equals 0.7. The incline of the plane is alpha, such that cos alpha equals 3/10. The box is released from rest, so we know u equals 0, and it slides down the plane, which reinforces the fact the friction acts up. After 0.5 seconds, the box reaches point Y. So we can say that t equals 0.5, where s, that distance we're talking about, is that x to y distance. Now the question asks us to find the velocity of the box at y. So whereas we know we started at rest and u equaled 0, in this case we're being asked to find out what v is, the final velocity. So at the moment we don't have enough information to use the Suvat equations, but we can use F equals ma to work out what the acceleration is. So to do that we need to think, well, it's going to be accelerating downwards as we know it moves down. What forces are acting parallel to this plane? I can see that there's a component of the weight, which I've just drawn in blue, and there's also the frictional force opposing that. So in this case, the resultant force is going to be that component of the weight, which is parallel to the plane, minus the friction. Let's work out what that component is. It's going to be equal to 2g times by sine alpha, because that side is opposite to the angle. So we use sine rather than cos. So our resultant force is going to be that 2g sine alpha minus the frictional force, because that's opposing its motion. And then that's equal to ma, and m in this case is 2. Now let's not forget that the frictional force equals mu r. We know what mu is, but we don't know what r is yet. R is going to be this force perpendicular to the plane. And we know that the box isn't moving in any of these directions perpendicular to the plane. It's not just jumping up or falling into the ground or anything. So therefore we can say that this R is equal to the perpendicular component of our weight. And that, because it's the adjacent of that triangle, is 2g cos alpha. So we can say by resolving perpendicular to the plane that R is just equal to 2g cos alpha. So if we return now to that frictional force equation, friction equals mu times R, we can say that friction equals 0.7 times by 2g cos alpha. We know what cos alpha is. We know that cos alpha is simply 3 over 10. So we just substitute that in place of cos alpha. Now we know that friction is equal to 0.7 times by 2g times by 3 over 10. Now putting that into the calculator, I end up getting 0.42g. And if you substitute it in, g equals 9.8, then that's absolutely fine, okay? There's no right or wrong here in terms of that. However, now we know what friction is, whether you've kept it in terms of g or not, we can substitute it into the above equation. And we're getting there now with working out what A is. However, we also need to know what sine alpha is as well. In a minute, we know that cos alpha is equal to 3/10. I know that cos alpha is adjacent over hypotenuse. So if I draw a little right angle triangle like I have over here, I can say that the adjacent is 3 and the hypotenuse is 10. Now using a bit of Pythagoras, I can work out what the opposite side of that triangle is. So that ends up being root 91. So as I know that sine alpha is the opposite over the hypotenuse then, I know that sine alpha equals root 91 over 10. So now I have everything I need to substitute into this equation here. I know what G is, I know what sine alpha is, and I know what FR is. So I am good to go. So let's do that then, let's get substituting. So here we have 2g times by root 91 over 10. And then I am going to minus FR from that. So I'm going to minus 0.42g. And that's equal to 2a. So now I can put this into my calculator using the fact that g is 9.8 and divide by 2 to get the a all on its own. And I end up finding then that a, the acceleration, is equal to 7.29 meters per second squared. So I'm going to fill in that information together with all of the other values that will be useful for Suvat. And now that I've got that acceleration, I can indeed now just crack straight on with working out what my velocity is. So I can see here that the most suitable Suvat equation is actually going to be v equals u plus at. So I'm going to write that down now, and then I can get started with making some substitutions. So v is what we want to find, and that's equal to 0 plus 7.29 times by 0.5. And so if I put that into the calculator now, I end up finding that that final velocity is equal to 3.645 meters per second. And that is exactly what we needed to get our marks. And so there we have it. That's another question which I hope you realise really just revolves around F equals ma and SUVAT. In fact, I would say that in mechanics, really, all we need to know is a little bit about vectors and the relationship between S, V, and A via differentiation. We need to know the SUVAT equations, we need to know F equals ma, and we need to know moments. And really, every single question will revolve around those. So long as you're good with your forces diagrams and resolving forces, then you should be absolutely fine with mechanics.
Oh, well done, lovelies. I'm really, really proud of all of your hard work.